Good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So this is a week 8 session, and today we'll be discussing about the week 8 topics, which are the free convection and heat exchangers. So let's have an overview of what are the topics that are covered in week 8. So a tutorial session for the internal convection flow, which we discussed in the earlier session, was discussed in the as a first lecture for week 8. We moved on to the free convection topic, where the equation for the governing equation for a free convection over a vertical flat plate was discussed. And then it's moved on to the heat exchanger part, where the heat exchanger, the definition of heat exchangers were discussed, and different types of heat exchangers were discussed, like parallel flow, counter flow, cross flow, and different orientations were also discussed. So basically, the heat exchanger is the device which is exchanges heat between two fluid streams. It can be gas to liquid, or liquid to liquid, or gas to gas. Different combinations can be out. Then the thermal analysis of heat exchangers were started, where the LMTD, that is the log mean temperature difference for parallel flow and counter flow, were discussed, and also basically the heat transfer in a uh, both parallel flow and counter flow heat exchangers were also discussed in the week 8. So let's discuss some of the questions based on this week 8 topics. So let's get started with the first question. So the first question is from this heat exchanger part. So it's the LMTD of a counter flow heat exchanger is 20 degrees Celsius. So LMTD is given. The cold fluid enters at 20 degrees Celsius and hot fluid enters at 100 degrees Celsius. The mass flow rate of the cold fluid is twice that of hot fluid, and the specific heat of the hot fluid is twice that of the cold fluid. So what is the exit temperature of the cold fluid? So let's just mention what are the given things. So the LMTD is given, that is the log mean temperature difference, is given as 20 degrees Celsius. The cold fluid, that is TCI, enters at 20 degrees Celsius, and the hot fluid enters at 100 degrees Celsius. So this is a counterflow heat exchanger. So if I draw a schematic, so this is selected be the which is of the length of the tube. So a cold fluid enters here, and hot fluid is like THI and THO, TCI, TCO. Okay. So, and also it is given that the mass flow rate of the cold fluid is twice that of the mass flow rate of hot fluid, and also it is given that the specific heat of at constant pressure for the hot fluid is twice that of the specific heat at cold fluid. So these are the given conditions or given things in the question. So we are asked to find out what is this one. What is the exit temperature of the cold fluid? Okay. So to find is TCO. Okay. So we know we will first apply the energy means energy balance equation. So whatever, if there is no loss, we are assuming the ideal condition. So an ideal condition where the heat exchangers are completely insulated, whatever is the heat lost by the hot fluid, it should be gained by the cold fluid. So if we equate the Q gain of cold fluid with Q gain, Q loss, Q loss of hot fluid, we will get m dot c CPC TCO minus TCI is equal to m dot h CPH THI minus TCO, because the cold fluid is gaining heat, and and the uh, hot fluid is losing heat. So, and it is given that we will substitute the given value. So it's 2 times m dot h CPC TCO minus TCI is equal to, it is given that the mass flow rate of the cold fluid is twice that of the mass flow rate of the hot fluid. And also it is given that the specific heat of hot fluid is twice that of the specific heat of cold fluid. So we can cancel out. So we get an expression that TCO minus TCI is equal to THI minus THO. This is a important expression. Means normally what we say is heat capacity. Heat capacity is defined as the product of mass flow rate and the specific heat. So we will usually define it as C. It's a capital P. Okay. So, if I'm referring to heat capacity as the uh, product of mass flow rate and the specific heat. So I may be using this term heat capacity in this session later. So please be familiar with that. The heat capacity is the product of mass flow rate and specific heat. So in this case, it is the both fluids have same heat capacity. Okay, this is a special case. A special case. Both the fluids have same heat capacity. So what will be the LMTD? It's if just what is the definition of LMTD? It is delta Ti minus delta To divided by ln delta Ti by delta To. Okay. So delta Ti is the here for it's a counter flow heat exchanger. So delta Ti is equal to Thi minus Tco and delta To is equal to Tho minus Tci. Okay. So if you, what is delta Ti? So delta Ti is Thi. So so if you use this equation, okay, we will get Thi minus Tco. I'm taking this value is here, and I'm taking this value Tho minus Tco. So I'm just rearranging equation 1. Okay, rearranging equation 1. So after rearrangement, I got it as delta Ti minus is equal to delta To. Okay, but if you apply this in the LMTD value, you will get 0 by 0. Means this is 0 and log 1 is also 0. Means delta Ti is equal to delta To. So the LMTD is not defined in this case. So if we apply Helmholtz-Hospital's rule, we will get that the LMTD of in this special case is equal to either delta Ti or delta To. Okay. So just if in some questions, say for example in some competitive examinations, if you found out that the capacity, the specific is not and not the heat capacity for hot and floor fluid is same, then you can directly use the LMTD. You can directly write the LMTD as delta Ti or delta To. So here we are asked to find out what THTCO. So we will write 20 is equal to we will write THI. So delta THI minus TCO. Okay. So TCO is equal to THI minus 20. So what is THI? that is 100, it is already given, minus 20, which is 80 degrees Celsius. So the answer to this question is 80 degrees Celsius. So, so the you have to what you have to think is it's a special case where the both the heat capacities of the cold fluid and hot fluid both are same. So under these situations, so we have LMTD is not defined. So by after applying Hospital's rule, we can write that the allotment temperature difference is equal to either the difference between this delta Ti, this difference of the temperatures at the inlet, or difference of the temperature at the outlet. So okay. So this is a counter flow heat exchanger. So parallel flow heat exchanger also we can apply the same method. So it's like same approach. Okay. So let's move on to the next question. So in a condenser, water enters at 30 degrees Celsius and flows at a rate of 1500 kilogram per hour. A condenser is at a temperature of 120 degrees Celsius and the cooling water leaves the condenser at 80 degrees. If the overall heat transfer coefficient is 2000 watts per meter square, we have to find out what is the area of the condenser. So it's like we have a tube. So here water is flowing inside the tube, and at the outside of the tube, condensation happens. Condensation happens, and the T surface, that is surface temperature, is maintained at 120 degrees Celsius. So it's like a flow through a pipe having constant uh, surface wall boundary condition. So if we connect it with the, means if you write, so this is the this is Ts, which is maintained at 120 degrees Celsius. So this is Tci, Tco. Okay. So this represents the temperature variations. So actually, this in these conditions where the temperature, where the some phase change happens, like steam is condensing or something, so that so the temperature of one fluid is not at all changing, or we can say that that fluid has infinite heat capacity. That is C tends to infinity. So the temperature is the temperature of the fluid does not change, so it is constant. Under that case, whether it is a parallel flow or a counter flow, it doesn't matter. So, so both parallel flow and counter flow doesn't matter. So that's why in this question it is not specified whether it is a parallel flow or a counter flow. So both have the same uh, problem. So let's move on to the question. So the given conditions are the mass flow rate is given. So 1500 kilogram per hour. If we convert into kilogram per second, it will come out to be, let's let it be like substitute at last. Then heat transfer coefficient is also given, that is how much, 2000 watts per meter square Kelvin. So TCI is given 30 degrees Celsius, and TCO is also given, that is 80 degrees Celsius. Okay. So what is general expression? Q is equal to UA, surface area of heat transfer, into delta TM, log mean temperature difference. So we'll find out the log mean temperature difference, that is delta Ti minus delta To divided by ln delta Ti by delta To. Okay. So delta Ti is 120 minus how much? TCI is 30. This is 80, 30 minus 120 minus 80 divided by ln 120 minus 30 divided by 120. So this will come out to be around 61.65 degrees Celsius. I'm not doing the math, that you can do it later. So the LMTD is given as 61.65. So now what we want to calculate is area of surface area of heat transfer. So this we found out. Okay, and U is also given. So what is Q? What is a heat transfer that happened? So we can consider the heat gain, that is m dot Cp TCO minus TCI. That is a heat gain by the whole fluid. So that is 1500 by 3600. So I am taking the specific heat as 4127 joule per kilogram Kelvin into what is temperature 80 minus 30. Okay. So this will come out to be around 85979.16 watts. So just equate this, because just as we know, the heat gained by the cold fluid should be this will be the heat transfer of the heat exchanger or the heat transfer of the system. So area is pi d into L. So we need to find out what is L. So equating this, we'll get what is 2000. It's given by diameter, I think. Okay, no need of this. This is, we need to find out what is AS. Okay, surface area of heat transfer. So AS into what is the log meter resistance, 61.65. So the AS will come out to be around 0.7 meters square. So in this case, we need to have a surface area of around 0.7 meters square for this temperature difference to happen at this mass flow rate. Okay, and this surface temperature. This was a simple question. I hope this is clear to everyone. So let's move on to the next question. The condenser of a steam power plant contains 1000 brass tubes of thermal conductivity 110, each of inner and outer diameter of 25 mm and 28 mm respectively. The steam condensation on the outer surface of the tube is characterized by a heat transfer coefficient of 10,000 watts per meter square. If the cooling water for a large lake is pumped through the condenser tube at 400 kg per second, if after extended operation, fouling provides a resistance of 10 raised to minus 4 at the inner surface, what is the overall heat transfer coefficient based on the outer surface? So here it's like so the question is, we have a condenser or a heat exchanger where it is used in a power plant to condense steam. So steam is the fluid. So steam condenses in the outer surface of the tube, and through the tubes, it is cooling water is flowing. Okay. So and because of extended operation, after long time of operation, some scale will form. Scale formation can happen on the tube surface. This scale formation will add an additional resistance to the heat transfer, that is known as the fouling. So usually fouling happens over after extended operation because of the scale formation, because of the impurities in the working fluid or the fluid which is passing through the tube. So after, it's like if we are installing the heat exchanger today, and after say 1 year, you will not get the same heat transfer or the same performance because of the fouling. So periodically we need to clean the heat exchanger tubes so that to remove the scale formation and to avoid the additional resistance caused by fouling. So that is basically fouling. So in this case, fouling is its inner surface of the tube is providing an additional resistance. So what we need to find out is the overall heat transfer coefficient. So we have a tube. Okay. This is a 25 mm. Outer surface is 28 mm. So cooling water is flowing through this. Okay. What is given? Like this, it is 1,000 tubes are there. So now we will be concentrating on a simple tube. So heat transfer coefficient will be same for 100 tubes or 1,000 tubes. So like we're assuming that all the tubes are identical. Okay. So you will write the heat transfer equation UI. Sorry. So the overall heat transfer coefficient UOAO should be equal to 1 by UIAI should be equal to 1 by HIAI. That is the inner surface we are having. Means we will start from inner surface. Inner surface there will be a heat transfer coefficient between the fluid and the pipe, and here we have to add the additional resistance of fouling resistance RF divided by AI. So if there in the question, if there is no fouling mentioned, we can avoid this term, that is RF. Then after that, there is a conduction resistance across this tube that we need to consider, that is Ln do by di 2 pi kl. So let the length of the tube be L, I'm assuming. And after the conduction resistance, it will be a convection resistance from the outer surface of the tube to the angle. Okay, so this is the total or the equation for the resistance network. Okay, so let I am writing A0. We are asked to find out based on the outer surface. So I am writing DOL. So the length of the tube I am assuming it is L. AI is pi DIL. So U0 pi D0L will be equal to 1 by HI by DIL plus RF by DIL plus Ln D0 by DI 2 by KL plus 1 by HO by DO. I am multiplying the entire equation by pi DOL. I will get 1 by U0 HI DO by DI plus RF DO by DI plus DO by 2 pi K. Sorry, there is no pi. I will get cancelled. 2K Ln DO by DI plus H1 by HO. So this is our equation for the outer overall heat transfer coefficient based on the outer surface area, or outer surface. So what all we know? We know DO we know, DI we know, sorry, DI we know, RF we know, again DO DI we know, DO we know, thermal conductivity of the tube we know, DO we know, DI we know, and HO is also given, that is the outer surface of the tube also given. So our task is to find out HI. What is HI? That is the inner heat transfer coefficient of the tube. For that, we have to go back to our internal convection chapter, where we discussed, or we will find out the heat transfer coefficient over an internal flow or a pipe. So first we need to find out whether this is a laminar flow or a turbulent flow. Then only we can use the some relevant or the suitable correlation. So the Reynolds number, we have the equation by 4 m dot divided by pi di mu. Okay. So this 4000 kilogram per second is given for the entire condenser. So for the each condenser, each tube will get, if it is equally distributed, 400 divided by 1000 is 0.4 kilogram per second. So each brass tube will get a non-flow rate of or a water flow rate of 0.4 kilogram per second. So I'm writing 4 into 0.4 pi into Ti. It is 25 into 10 raised to minus 3 into mu is given. What is the properties of water is given, and 0.6 into 10 raised to minus 4. Okay. So the answer to this question is, we will get the value of Reynolds number as 21,231.4. Okay. So this is a turbulent flow. So we have to use the Bitterboiter equation. That is, Nu is equal to 0.023, Reynolds number raised to 0.8, Prandtl number raised to 0.4. Or we can Hi is equal to K divided by L, K or divided by not L, Di, 0.023, Reynolds number raised to 0.8, Prandtl number raised to 0.4. Okay, what is K? K is given as 110, right? 110 divided by Ti is given 25 into 10 raised to minus 3, 0.023. Reynolds number is given 2123, or we find it out the Reynolds number 0.8. Prandtl number is given how much? 0.6. So the heat transfer coefficient, after calculation, the heat transfer coefficient will come out to be 3399 watts per meter square. So this was our main part in this question. So to find out Hi. Now everything is given. Just need to substitute to equation 1. This is question. Just substitute Hi to equation 1. So after substitute 1 by u0 is equal to 1 by 3399 into di is 20, dod is 28 divided by 25 plus rf is given 10 raised to minus 4 into 28 divided by 25 plus do is given 28 into 10 raised to minus 3 divided by this. This I have not put 10 raised to minus 3 because it is just a ratio. So you just need to careful in the units. So here it's not ratio, so it's like we have another ratio. It's ln 28 divided by 25 plus 1 by 10,000. Okay. So answer will come out to be 5.554 into 10 raised to minus 4. So the outer surface heat transfer coefficient rho0 is equal to, if you take the inverse, you will get 1800 watts per meter square. So this was our question. So the main thing we need to consider is here, the main uh, part we need to find out in this question is the internal heat transfer coefficient. Okay. And also in some cases you may not, in the question there may not be any fouling case. So you can avoid this RF term. That is what is I have written. That's just fouling resistance. That is the fouling resistance. So in some cases, in some questions, it may not be given. So you can avoid that fouling resistance. Okay. So I hope this question was clear. So we will go to the next question. A cold water enters a counterflow heat exchanger at 10 degrees Celsius at a rate of 8 kg per second, where it is heated by a hot water stream that enters the heat exchanger at 70 degrees Celsius at a rate of 2 kg per second. Assume the specific heat of water to remain constant 4.18 kilojoule per kilogram. Determine the outer temperature of the cold and hot streams for this limiting case. Okay. So the limiting case in the sense, what it means is that we need to find out the maximum heat transfer or the maximum uh, temperatures that the cold and hot streams can attain under for this. Okay, that is for the limiting case. So that is we need to find out the maximum cold and hot water temperature, outlet temperatures for the cold and hot water stream that it can have. It can have. So for that we need to find out. We uh, need to find out the maximum possible heat transfer. We need to find out what is the maximum possible heat transfer. So let's take the example of the counterflow itself. Okay, I'm drawing a counterflow heat exchanger. Okay, so water is entering and the cold and hot fluids are exchanging heat THI, THO, TCI, TCO. Okay, so and the heat capacity that is C, hot fluid is MC, MHCP means both are water. So I am writing the same. Okay, and C is MC, C is this, that is heat capacity. Okay, so what is the maximum possible heat transfer in this case? Okay, so let's consider two cases. First case, so we know Q is equal to, or we will write the general expression. The heat transfer in the hot side is CH THI minus THO. QC is equal to CC TCO minus TCI. Okay. So the first case is assume that CH is greater than CC. Okay. Then obviously that is the temperature difference across. This I am writing this as DTH and this is DC. TC. That is a temperature difference between cold or hot and means temperature difference in the hot stream and the cold stream. So DTH should be less than DTC. Okay. If the heat capacity of the cold fluid is more than the hot fluid. So or when this maximum heat transfer happens in a counterflow heat exchanger that I forgot to mention at the initial. So in a counterflow heat exchanger, what happens is when if the length of the tube is infinite, if the length of the tube is infinite, at that case, at that ideal case, we have the maximum possible heat transfer, right? So in this case, what happens is the CC, that the specific heat of cold fluid is lesser. So maximum heat transfer, maximum temperature difference happens between the cold fluid. So what is the maximum temperature difference it can happen in the cold fluid? So that the cold fluid, uh, the outlet temperature of the cold fluid can have will be equal to the inlet temperature of the hot fluid. So for maximum heat transfer case, TCO will be equal to TCI. That is the maximum possible heat transfer it can have. If the CH is, or if under this case, when the specific heat is of the hot fluid is more than the cold fluid. So we know Q max is equal to Cc into TCO minus TCI. So instead of that, I can write Cc into THI minus TCI. Okay. On second case, if Cc is greater than Ch, then a temperature difference across DC, that is a cold stream, will be less than that of the hot stream. So at the same case also, for maximum possible heat transfer, what happens is the TH exit should be equal to TCI. That is the maximum possible heat transfer can happen, because the cold fluid cannot cool down, or the hot fluid cannot cool down below the temperature of the inlet temperature of the cold fluid. So this is if the if the specific heat capacity of the cold fluid is more as compared to hot fluid, hot fluid is less as compared to cold fluid, then maximum possible heat transfer takes place within the hot fluid. So what is the maximum temperature it can attain for the hot fluid? It is the inlet temperature of the cold fluid. So in this case, Qmax will be CH times THO minus THI. So it is, opposite. THI minus THO. So CH into THI minus TCO. You see, this temperature difference both are same. So the maximum possible temperature difference is in both the cases, the maximum possible temperature difference is same, that is THI minus TCO. So in general, we can write for maximum possible heat transfer, that is Q max is equal to C min, whichever heat capacity is minimum, whether it can be hot fluid or cold fluid, minus THI minus TCO. Okay. So let's see what is in the for this question. So as both are water, just we need to check which has maximum flow rate or minimum flow rate. So the C min will be the hot stream, that is which is at a which has nearest 2 kilogram per second. So C min is equal to CH, which is m dot h into Cp, it is 2 into 4180, which will come out to be 8.36 kilowatt per liter. So from in the question it is asked Q max, which is C min into THI minus TCI. Okay, so actually this question should be mixed. Sorry, it's a mistake from my side. So the question should be the maximum determine the forget to put the last part. Determine the maximum possible heat transfer. This should be the question. So determine the maximum possible heat transfer. So Qmax is equal to C min into, that is 8.36 10 raised to 3 into CHI, what is the entering temperature of hot fluid, uh, 10 70. Okay, 70 minus 70 minus 10. Okay. So this will come out to be 502 kilowatts. So, and this question only, so we are asked to find out the maximum possible heat transfer. Okay. I hope that was clear. So it's like a conceptual question. So this concept is discussed in both Opera and Sencher. So you can further read in the heat exchanger uh, uh, chapter of both the textbooks. Okay. I hope my explanation was clear to you. So if you have any clarification, if you need any clarification, you can further refer to the text. So let's move on to the next question. So it's a consider a 0.6 meter thin square plate in a room of 30 degrees Celsius. Okay, this is from the natural convection path. One side of the plate is maintained at a temperature of 90 degrees Celsius, while the other side is insulated. Assume natural convection is the only mode of heat transfer. Determine the convection heat transfer and the rate of heat transfer, convecting heat transfer coefficient, and the rate of heat transfer from the plate. Okay. So in the question, we have a plate, vertical plate. Okay. So one side is insulated, and the other side is having a temperature of 90 degrees, and it is transferring heat by convection. We are asked to find out the heat transfer coefficient and also the rate of heat transfer. So the properties of the air is also given, and the Nusselt number is also given. This correlation is known as Churchill and Chern correlation and Schuh correlation. So first we need to calculate what is the Rayleigh number. So Rayleigh number is equal to Grashof number into Prandtl number. So what is Grashof number? G beta delta T L cube divided by mu square into Prandtl number. So first we need to calculate what is the Prandtl number. Okay. So what is beta? Beta is the coefficient of expansion, volumetric expansion. So it is 1 by Tf, that is a film temperature. So one you should think is, you should consider is Tf should be in Kelvin. Okay. So what is the Tf here? Tf is equal to Tf is equal to 90 plus 30 by 2, which is 120 by 2, which is 60 degrees Celsius. Or what is when we convert it into Kelvin, it will become 3315 degree. Sorry, Kelvin. So substitute this Rayleigh number, that is gravity 9.1 into 1.33315. What is the temperature difference? It is 90 minus 30. It is T infinity is at 30 degrees Celsius. And the length is given as 0.6 cube. What is the NMS degree viscosity? 1.896 into 10 raised to minus 5 the whole square. And what is the Prandtl number? 0.7207. So if you calculate, you will get it as 7.656 into 10 raised to 8. This is the value of the Rayleigh. So just substitute this into this equation. You will get the value of Nusselt number, that is Nu is equal to 0.825 plus, that is 0.387 into 7.656 into 10 raised to minus 10 raised to 8 raised to 1 by 6 divided by 1 plus 0.492 by Prandtl number 7207 raised to 9 by 16 plus, sorry, the whole raised to 8 by 25 whole square. So if you calculate this, you will get the value of Nusselt number as 113.4. So from Nusselt number, you can find out what is heat transfer coefficient A by L, which is 11.4 into the thermal conductivity is given 0.0280 divided by what is L, 0.4, 0.6. You will get it as 5.306 watts per meter square. And also we are asked to find out what is Q, which is H A surface into T S minus T infinity. The surface area itself square, that is 0.6 into 0.6 into Ts 90 minus T infinity 30. So you will get it as 115. So this was nothing. So just what we need to do is we just need to find out the Rayleigh number. The correlation was given. So these Nusselt number correlations are, as you see, it's very complex like this. So mostly in the examinations, in university examinations, you may be, I don't know, you may be allowed to use heat transfer data books, but in competition examinations, if you want, they will give the, mostly they will give the correlations like this. So I hope this was clear. So we'll just move on to the next question. So it's a 25 stainless steel board is moved from oven at uniform temperature of 300 degrees Celsius. So the ball is then subjected to flow of air at 25 degrees Celsius with a velocity of 3 meters per second. The surface temperature of the ball drops to 200 degrees Celsius. Determine the average convection heat transfer coefficient used in this cooling, during this cooling process. Okay. The Nusselt number is given, so, and also the properties are also given. So we have a board which is initially at 300 degrees Celsius, and air was allowed to flow at 3 meters per second, and the temperature of the air is 25 degrees Celsius. So we have to find out the Nusselt number. Okay. So what is we have to find out what is H. So for that, we are already given with the value of Nusselt number. We need to find out what is the Reynolds number, that is of the flow of air, that is V T by mu. V is already given, which is 3 meters per second, into diameter is given 25 centimeters. It's not uh, 25 mm or 25 centimeters. Yeah, it's 25 centimeters over. Okay. So 0.25 the whole square. Sorry, it's no whole square divided by mu. It is the properties of air 1.562. So we will get the answer as 4.802 into 10 raised to 4. We will get the Nusselt number as this much. Yes, now just we need to calculate the before we already got the value for Nusselt number. We just need to substitute these values in the Nusselt number correlation. So you can see there is one viscosity correction factor is introduced. So this viscosity correction factor is introduced when there is a large variation in the viscosity. You can see that on the surface where the temperature is higher, the viscosity is different, and when the core at the core or there will be a very large variation between the viscosities between the higher temperature and the, if in this case it is a freezing temperature and the surface temperature. Okay, you can see how much variation is there. It's like, so there is a large variation in viscosity. Sorry, this one. So there is a large variation in the viscosity. So we need to account for the viscosity correction factor also if there is large variation in viscosity between the temperatures. Okay. So a similar type of question was discussed in the lectures. So you can just move on and refer to that for further clarification. So here we need to incorporate the viscosity correction factor. So this correlation to point is zero point 0.4 times. The Reynolds number is given 4.802 10 raised to 4 raised to 0.5 plus 0.06 Reynolds number by 2 by 3. Sorry. Or 802 10 raised to 4 raised to 2 by 3. Prandtl number how much? 0.7296 into mu infinity 1.849 into 10 raised to minus 5 divided by dynamic viscosity as the dynamic viscosity at the average surface temperature 1 by 4. Okay. So if you calculate this, you will get the value of Nusselt number of 135. So just it is nu k by d. It is 135 into what is the thermal conductivity of the board. Sorry, not board. It's a thermal conductivity of the stream. That is the fluid. 0.0255 by diameter is 0.25. So the answer will come out to be around 13.8 watt per meter square. This is the average heat transfer coefficient based on the during this cooling process. So in the next question is also a continuation of the previous question. So in this question, we need to estimate how long this process of cooling will take place. Okay. So means uh, from the surface temperature to drop from 300 to 200 degrees Celsius. That is what subject is given in the question. We need to find out what is the how much time it will take. Okay. So let's find out the average heat transfer coefficient. So to estimate the time of cooling, we need to determine the average rate of heat transfer from the Newton's law of cooling using the average surface temperature. Okay. Average rate of heat transfer. This is a transient process. So in real cases, we need to do the transient heat analysis, but we are just doing an approximation here. So we are taking the average rate of heat transfer. Average rate of heat transfer by using average temperature. Average surface temperature. Surface temperature. So what is T average surface? It is 300 plus 200 by 2, that is 250 degrees Celsius. So Q average is equal to H A surface into T average surface minus T infinity. So H is we already calculated how much 13.8 into the surface temperature, surface area of the sphere is 4 by 4 by r square. So if you convert it into diameter, it will become 5 d square. What is diameter? 0.25 whole square into 250 minus what is T infinity? Is 25. Okay. So the answer will come out to be 609.52 watts. So this is the average heat transfer from the average rate of heat transfer from the board. So let's see what is the total. So how much energy it lost by simply we can find out how much energy it is lost by the means sensible heat change. Okay, by the heat change of the specific heat change of the uh, body. So we can write Q of body. It's not rate because it's a solid. Q bod is equal to mass of the into Cp delta T. Okay. So we will simply uh, assume that this is pulled from 300. So what is the uh, heat loss? That what is the uh, energy change? In an energy change of the body from cooling from 300 to 200. So mass is given, that is rho A V, that is rho. Sorry, there is no V. It's like sorry rho into the volume Cp delta T. Density is given that 8055. The what is the volume of the fluid of the sphere? It is pi by 4 d square, pi by 6 d square, d cube. Sorry. So what is the diameter? It is 0.25 the whole cube into what is Cp is also given. It is 480, right? Into 300 minus 200, right? Yeah. So the the energy or the energy it is lost by the ball. We'll find out as 113,316 200. You can do. I'm not doing the calculation, so you can just cross verify this also. So this is the you just see the uh, units, that is here it is joule. This much energy it is lost by the ball. So this is the rate of that energy loss, right? This is in how in 1 second how much energy is lost is specified by this calculation. So this is the total energy that is lost by the ball because of this cooling. Okay, so what is this? So the heat transfer is the rate of energy change. Okay, so that is delta T, or the T for cooling, is equal to Q ball divided by Q dot total, Q average. Sorry. 316,300 divided by joules divided by 609.52. What is watts? It's joule per second. Okay. So this answer will amount to be around 19.65 seconds. So this much seconds it will require to cool down from 300 to 200 degrees Celsius. So in this calculation, we assume that the entire surface uh, of the ball, entire ball is at 200 degrees Celsius, which may not be, it is not necessarily true. So the inner region may be at a higher temperature than its surface. So that we discussed already in the uh, what to say, in the transient heat conduction part. So we just need to check the Biot number and all. So here, just for the means in the just for the case of simplicity, we assume that the entire ball is at a isothermal condition, which may not be true because there will be a transient variation of the temperature within the ball. So that will make the question more complex. So, but in order to simplify the question, we are asked to in this question it is asked to take it as a like a isothermal case. So those who want to, they can also apply uh, the transient conduction part. You can find out the Biot number, and I already discussed how when the Biot number is greater than 0.1, how we can find out the heat transfer coefficient. how we can find out the heat transfer, temperature distribution, the heat transfer, etc. is already discussed in the previous classes. So you can also try by this method, and you can have a comparison between this approximate method and the accurate method. What is the error at? Okay, so that's the end of this session. So I hope this session was helpful for you. So so we will meet in the next Monday, the same time. Thank you, thanks for your uh, participation, and thanks for watching, joining this session. And thank you very much once again, and have a nice week ahead. Thank you.